Hello dear students, we are once again with a video on two-dimensional continuous random variables. We'll be discussing two more problems on the topic two-dimensional continuous random variable. First question, the joint PDF of xy is f of xy is equal to 1 by 2 in the interval in the region x greater than 0, y greater than 0, x plus y less than 2 and equal to 0 otherwise. The questions are check whether x and y are independent. Second question, find probability x plus y less than or equal to 1. Third question, find probability x less than or equal to 1, y less than or equal to 1. And the fourth question is find probability x greater than 2y. So we are considering all these questions one by one with respect to the region x greater than 0, y greater than 0, x plus y less than 2. Let us see how this problem can be worked out. This is a function, this is a PDF, joint PDF given fxy is equal to 1 by 2 for x greater than 0, y greater than 0, x plus y less than 2 and 0 otherwise. First question is to check whether x and y are independent. So for that, we are going to first find the marginal density function of x and y. So marginal density function of x and y, x is integral over y fxy dy. So we are keeping x as a constant, x temporarily as a constant, and we are integrating with respect to x. And you know, when x is kept temporarily as a constant and integrated with respect to y, we are actually considering a vertical strip in this region, and hence we are integrating from the lower point of this vertical strip, which is y equal to 0, to this maximum point where y is equal to 2 minus x, and y equal to 2 minus x is obtained from the equation of this line x plus y equal to 2, and hence we have integral 0 to 2 minus x half dy, which is 2 minus x by 2. Now we have to find the second one, marginal density function over y. So that is obtained by integrating f of xy with respect to x for all the upon the limit of x. So in that case, we have to consider, since we are integrating with respect to x, keeping y as a constant, we will be considering a horizontal line or a horizontal strip in this region of integration, and the limits are set according to this horizontal strip. The lower limit of this horizontal strip is x equal to 0, the y-axis, which is x equal to 0, and the maximum point is x is equal to 2 minus y. Again, x is equal to 2 minus y is obtained from the equation of the line x plus y equal to 2. And hence we have, on integration and substitution of the limits, we have 2 minus y by 2. So you can see that fxx into fyy is not equal to fxx into fyy is not equal to f of xy. And hence you can show that x and y are not independent. So that completes the first part. We have to check whether x and y are independent, and if fxx into fyy is equal to f of xy, that shows x and y are independent. Here that's not the case, so we have proved that x and y are not independent. Now the second question. We have to get the probability capital x plus y less than or equal to 1. We have to get the probability x plus y less than or equal to 1. See, this whole region is defined by the PDF in the question. And in this particular subpart of the question, we have to find probability x plus y less than or equal to 1. So basically our region remains the same, and here we have to consider this question, and according to the question we need to set the region according to this question, and hence we have the region as determined by x greater than 0, y greater than 0, x plus y less than 2 and x plus y less than or equal to 1, and hence we are restricted ourselves to this blue shaded region. So this blue shaded region is a region of integration when we consider probability x plus y less than or equal to 1. Remember, the basic region remains the same. The basic region is given in this portion. This whole portion, this whole bigger triangle gives a basic region defined as per the joint PDF. And since according to this particular question, we have to be restricted to the region which is also determined by x plus y less than or equal to 1, and hence we are restricting ourselves to this blue shaded region. And therefore, in this region, we are going to integrate. We have to consider the joint PDF 1 by 2. We have to make use of double integration since we are going to consider both x and y. So you can integrate according to your choice. Here I am integrating it in the order dy dx. First integration is with respect to y, keeping x as a constant. And that is why I have drawn a vertical line over this region, and the lower point of the vertical region is f, which falls on this x-axis, which is y equal to 0. Maximum point is g, which falls on the line x plus y equal to 1, hence we have y equal to 1 minus x. And then, so the inner limits are y equal to 0 to 1 minus x. In the next part of the integration, you have to slide this vertical strip from the lowest point of the region, which is BD. The equation of BD is x equal to 0, and we have to slide the strip from the lowest point of the region, entry point of the region, which is BD, to the exit point of the region, which is E. The equation of this point E is given by x equal to 1. So the outer limits are set as x equal to 0 to x equal to 1. So we integrate. It's a very simple procedure, and we get the final answer as 1 by 4. Then the next part of the question is probability to find probability x less than or equal to 1, y less than or equal to 1. Again, the basic region is the same, the region determined by the PDF x greater than 0, y greater than 0, and x plus y less than half. So this portion, this bigger triangle gives a basic region. And here we have to consider the region given by the question. The region given by the question is x less than or equal to 1. This is a line x equal to 1, x less than or equal to 1. So this portion is x less than or equal to 1. Then y equal to 1 is this straight line. Y less than or equal to 1 is this portion. So the region determined by the region defined by the initial, by the basic PDF, basic joint PDF, and the region together with the region determined by x less than or equal to 1, y less than or equal to 1 is this simple square region. And here we are going to integrate. So the lower limit of x is y is 0 to the maximum limit 1. So the lower limit of for the outer integration, we have to slide this strip from x equal to 0 to x equal to 1. So this is a very simple procedure since the region of integration is a rectangular, it's a square region. So we can just substitute the limit according to the values that we have. And so it is integral 0 to 1, integral 0 to 1, 1 by 2 dy dx, and the answer is 1 by 2. So that completes the third part of the question. Now the fourth part, we have to get the probability capital X greater than 2y. So capital X greater than 2y is the next region that we have to consider within the given region determined by the given PDF. So as usual, this larger rectangle is our former rectangle, the region in which the joint PDF is being defined. And here we are attaching, we are drawing the new line x equal to 2y. This is a line x equal to 2y. So x greater than 2y. So this is this lower portion is a region determined by x greater than 2y. So we have to consider the feasible region to x greater than 0, y greater than 0, x plus y less than 2, and x greater than 2y. So the feasible region is a region defined, determined by this blue shaded region. So this is a feasible region according to this question. Okay, so now in this region, we are going to integrate. Again, we need double integration. In this double integration procedure, we are setting the order according to the convenience of the region. So for this particular region, if we draw a horizontal line, that will be more convenient, because instead, if you draw a vertical line, you will have to divide the region into two, and hence you have to do the double integration procedure twice. So instead of avoiding all such difficulties, I am drawing a horizontal line in this region of integration. And the advantage of this horizontal line is this single horizontal line is enough to cover this whole blue shaded region. So it is better to draw this horizontal line within the region of integration, and this determines the order. Horizontal line means y equal to constant, and y equal to constant in the integration with respect to x, and therefore we set the order as dx dy. Hope you understand this procedure. This is a triangular. This is, even though this is a triangular region, it has 1, 2, 3 boundaries, 1, 2, 3 boundaries, and the two boundaries are not horizontal and vertical lines. Therefore, we have to be a little bit careful while integrating along this region, integrating in this region. So that is why for our convenience, that is why we have set the order as dx dy, because we have to, it is better to consider a horizontal strip rather than a vertical one. So in this horizontal strip, the lower portion, the lower limit is E, maximum value is F, and the lower limit E is determined by the equation x equal to 2y. So x equal to 2y is a lower limit. Then the maximum value of this line falls on the line x plus y equal to 2, and therefore f is determined by the equation x is equal to 2 minus y. Okay, and then the outer limits of integration are obtained by sliding this horizontal strip from the lowest point of the region, or the entry point of the region, to the maximum point through which we have to exit this particular region. So the lowest point is determined by the line by the x-axis, whose equation is y equal to 0. The maximum point is determined by the point of intersection of x plus y equal to 2 and x equal to 2y, and hence we get the maximum point. The coordinates of this point is 1.33, 0.67, and this 0.67 is actually 2 by 3. So I've just put it as 2 by 3 itself, or rather you can put it as 0.67 also. So y equal to 0 to y equal to 0.67 or 2 by 3. So this has to be integrated. The integration procedure is very simple. The first integration, 1 by 2 into integral dx is simply x between the pair of limits. So we have 2 minus y minus 2y dy. And after the next integration and substitution of the limits, we have the final answer as equal to 1 by 3. So we completed the whole question. We completed the 4 parts of the given question. So hope you understand this particular question. And now the next question. A pair of random variables, capital X and capital Y, have a joint PDF given by f of xy is equal to 1 by pi in the interval in the region x square plus y square less than or equal to 1 and 0 otherwise. Show that x and y are not independent but uncorrelated. So first part is we have to show that they are not independent. So whether they are dependent or independent, the procedure is to find out the marginal density function of x, marginal density function of y, and we have to check whether the product is equal to the original PDF or not. So let us check it step by step. Fxx, marginal density function of x, is defined as integral over y fxy dy. And see, this region under consideration is a circular region determined by x square plus y square less than or equal to 1, the region inside the unit circle. Now here we are going to integrate with respect to y. Integration with respect to y keeps x as a constant temporarily. When x is a constant, we have to consider a vertical line within the region of integration. So this vertical line is being considered. The lower point of the vertical line is a point on the circle. Similarly, maximum point is also a point on the circle. For the lower point, y square is equal to 1 minus x square. So y is equal to plus or minus root of 1 minus x square, and minus root of 1 minus x square is the value for the lower limit, because the lower limit falls in the fourth quadrant. Their y is negative, so we have y is equal to minus root of 1 minus x square. The topmost point C is in the first quadrant where y is positive, so the maximum value is y is equal to root of 1 minus x square. Integral minus root of 1 minus x square to plus root of 1 minus x square 1 by pi dy. So after integration, it is simply 2 by pi root of 1 minus x square, and that the limit of x is from minus 1 to plus 1. So that is fxx. Now fyy definition, integral over x fxy dx. Since we are integrating with respect to x, keeping y temporarily as a constant, we are drawing a horizontal line in this region of integration. For the horizontal line, the lower point is C, determined by x is equal to minus root of 1 minus x square. We know x square is equal to 1 minus y square. So x values are plus or minus root of 1 minus y square. And for C, which falls in the second quadrant, x is negative. So we have the lower limit as minus root of 1 minus y square. For D, which is a maximum value of this horizontal line, it falls in the first quadrant where x is positive, and hence x is equal to root of 1 minus y square as a maximum value. So after integration and substitution of the limits, we have 2 by pi root of 1 minus y square, and the limit of y is from minus 1 to plus 1. So that completes the marginal density function of y. Now, obviously, you can see that this fxx into fyy is not equal to 1 by pi. And therefore, x and y are not independent. So, x and y are not independent. So, that completes the first part. Now, the second part, we have to show that x and y are uncorrelated. X and y are uncorrelated if covariance xy is equal to 0. And covariance xy is equal to exy, expectation of x into y, minus expectation of x into expectation of y. So we are going to evaluate them one by one. Expectation of xy is double integral xy f of xy dy dx or dx dy. So it is equal to 1 by pi. The order is set as dy dx. So the inner limits are for y. Y is equal to minus root of 1 minus x square to plus root of 1 minus x square. Hope you remember the region under consideration. The region is the circular region. And therefore, the limits are y equal to minus root of 1 minus x square to plus root of 1 minus x square. And then x ranges from minus 1 to plus 1. We have to consider the full circle. Xy dy dx. And obviously, in the first integration with respect to y is a xy is an integrand. X is obviously a constant in the first integration procedure. Y, it's an odd function, and hence its integral between a minus L to plus L. For an odd integral minus a to plus a f of x dx from minus a to plus a, integral fx dx is equal to 0. So this is a property of odd integral, and hence we have the whole expectation of xy is equal to 0. See, here we have applied the property of odd functions, the integral of odd functions between the limit minus a to plus a. Now expectation of x is integral x fxx dx. So integral minus 1 to 1 x into 2 by pi root of 1 minus x square dx. In the earlier slide, we have obtained fxx as 2 by pi root of 1 minus x square. So that is substituted here. Again, the property of odd function x into root of 1 minus x square being an odd function of x, its integral from minus 1 to plus 1 is equal to 0. Similarly, you can show that expectation of y is also equal to 0. So, hence obviously covariance xy is also equal to 0. Therefore, you can prove that x and y are uncorrelated. So, hence we conclude that even though x and y are dependent, they are uncorrelated. So, that completes the answer to the second question. Thank you.